Hello. Good afternoon, everyone. Can you hear me? Can you hear? Let me see. Yes, nice. Bravado. Thank you. Thank you, thank you, thank you. Perfect. So it's weekend again. May I remind you, this is a week number 4, lecture B. And this is Friday. And this is the first day of the year of what? Yes, nice. How come? I didn't know. You know, Lunar New Year, first day. Happy New Year. Okay, so everybody, so we have 41, 40. We should have another 20 students. So let's wait just a little bit. So here's the plan, what I want to do. The first, I'm going to go through with you the quiz last, this Wednesday quiz A. I'm going to go through the reasoning about the logic behind that. Then after that, we are going to go through the opamps with capacitors or inductors. Okay, but in between, we are going to revisit the magic 4-letter called CMRR. What is CMRR? Common mode. Yeah. Wednesday, another trick quiz? No, it's a very normal, not trick at all. So I'm going to share my screen and let's start the interesting journey. Let me hide this thing and show you this. Do you see a circuit in your screen? Shall we make this one a little bit bigger? Okay. So you need to tell me what you had a grade for the circuit theory. Don't you feel my humor here? Okay, so it's funny. Well, let's start to do this problem. Maybe smaller one more time here. So VA plus is V in, okay? Why? Because there's no current flow into op-amp. So there's no current flowing into here, right? So then there's no voltage drop on this 5K ohm, right? So this guy and this guy are the same. Okay. So now we are going to say VA minus, we're talking about this one, VA minus equals what? VA plus, because what? Because the idea op-amp. Because in the ideal op-amp, the difference between here is almost 0. Make sense? Okay, infinite gain. Okay, so you can say that. Thank you, actually. Yeah, great. So can continue to say VAO. What is VAO in here? What is VAO in here? It's also VA minus. This guy and this guy are the same. Why? Because there's no current in here, and this is actually V in, okay? VA minus is VA plus is V in. So V in and this is also V in, so the current here is 0. Current here is also 0. So do you think this current is 0? Across the 10K ohm, the current is also 0. So you have that there's no no voltage drop. So this is also V in, right? Then what is it? Because no voltage drop. Voltage drop in 10 km, 10 ohm. Okay. So far, you agree with me? Okay, let me see. Resistor don't matter. Yeah, yeah. There's no voltage drop, no current flowing. Then we know that these two ends, the voltage difference is 0. Okay. So therefore, V in is V in. V in minus V in is 0. Okay. So this is VAO is V in. So this is V in also. You agree? Okay. So let's make it smaller so we can see it. So then VB, so what is the VB? VB plus is this guy, right? This guy. What is the voltage here? Because this is 0, is a ground. So this is a V in. So it's 1/3 is a 5 divided by 10 plus 5, right? So it's 1/3 of V in because there's no current flowing. There's no current flowing in here. This is 0, as if there's nothing going there. So then everything is going here. So it is an ideal voltage divider, right? So we are going to talk about VB. What is VB then? VB minus. What is VB minus? This is VB plus. No question about it, because again, this is ideal opamp. Okay. Okay. So I know that this is 1/3 of V in, right? Okay. 1/3 of V in. All right. So then what is the current in here? So VBN equal to KCL here. This is the current is 0, right? So then this V in minus 1/3 of V in. Yeah, this is a 2/3 of V in divided by 10, right? So it's a 2/3 of this is 1 minus 1/3. So it's V in minus 1/3 of V in is a 2/3 of V in, right? Divided by what? 10 k ohm, right? So this is 10 k ohm. So that's the current. Let's say this is the current I. This is the I. So, and this is this direction, right? This direction. So what is, suppose you have a current from here to here, okay? So then this is also I, right? Because the offset, this direction offset is minus I. Offset minus I plus I is 0, right? So this is KCL, right? So in other words, we know that, yeah, we know that, let me use the red one. V out minus VB. VB is 1/3 of V in, right? Divided by 5. Okay. This guy minus this guy, add this guy, it should be 0. So plus this I, plus this term. This is the I. V out minus VB minus. So this guy, put it here, plus this one must be 0. Then what is V out? Because if you cancel this one here is 1, this is 5. So this is the same as this one, you cancel out. So V out is Make sense? V out is 0. So the answer is 0. Did you do it correctly? V out is always, I put always there to give you a hint. It's always, okay. Isn't this question very interesting? And you can do it if you follow the correct logical reasoning. And if you follow the ideal op-amp assumptions. And plus KVL, KCL, you know it. So, did you get it? Question? Is this hard? I didn't do it correctly. Yeah. I understand now though. Okay, good. This is what I want to hear. What if there is no voltage in V out? What is, only that I got right was picking up my grade. Are you joking? I assume there was a voltage drop. Wait, if there is no voltage in V out, is there any point to the op-amp? Now, this is just the game. Don't ask me what's the real purpose of that. It's just no, there isn't no utility. I don't know the utility in how this is useful. Okay. So there's another one. Okay. All right. So it's not so hard, right? So today you are going to do a quiz like this. You should be able to get this one. I already asked you how to do this. You already know how to do. Write down. And then you'll see that the first one is a negative resistor. Possible? Possible. Yes. So if I check V and I, so the basic idea is if we treat, listen carefully. If I treat something like this, so you have I, you treat everything like this, and so you have V in here. So this black box is like this black box. Okay, it's like this black box. So this is a kind of a artificial component. Using op-amps, you can construct something that strangely here, strangely. This is a negative resistor, okay? Negative resistor. So previously, if I put R in here, I know that V is R times I. But in this case, we can actually have something V equals minus R times I. So this minus R becomes what I call a negative resistor. A resistor with negative resistance. How this is possible? Yeah, this is the realization curve for you. You can see it. So keep doing it. Okay, it's fun. I'll explain everything else next lecture. Okay, so enjoy this. All right, so let me see. I do this. If I do this and this. Okay, so let's do it. Oh, okay. All right. Let's start from here today about CMRR. Okay. Really? Why this is still here? Oh, let me remove this. So we are talking about a common mode and a differential mode. So for amplifiers, they could be non-ideal. In real world, there's no idealized op-amp. So in this case, what is the most important quality factor? That's called CMRR. So we are going to go through it today. So if it is ideal, then the V out is the difference of them. Okay. Okay. But in reality, so here, in reality, this is not the case. Maybe we already appreciate it. If the resistors, there's no exact same resistor, okay, in theory, because the resistor is also randomly, resistor value is in between an interval minimum and maximum. And in this interval, we use this notation to say this value in between. There are infinite possibility inside this interval, right? So it's random actually. It's plus or minus 5% or plus or minus 10%. So in that sense, it's hard to find two identically the same resistance. Okay, there's always a difference. Then this differential will never be zero, even if they are zero. So we are going to split them into two types. One is called common mode. Another one is called differential mode. Okay, so let's move on. And then for this, in general, we have this type. Okay, this type. So this is a superposition principle, right? Superposition principle. So we hope we are going to write this A1, A2 in terms of A common mode and differential mode. See how we can do that. So we did this one here. So first of all, we assume the V1 and V2 are the same. Okay, V1, V2 are the same. V in, okay, same V in. Then we know that the output of the common mode, common means V1 equals V2. This is called common mode. Common mode. Then because you have this file the same, you put here is a V in, okay? So V1 and V2 are the same, okay? So in this case, then we based on a previous slide, we know that the V out is A1 V1 plus A2 V2, because V1 equals V2 equals Vn. So then we call this A1 plus A2 is ACM, common mode. Okay, common mode. So in this way, you know that what is the common mode? Amplification coefficients. It's A1 plus A2. But what if you make V2 minus V1 the difference? V2 and V1 are the same, but it's opposite sign. It's opposite sign. V1 is V2 is opposite sign. Then that is a V in, okay? So you know that V1, if V2 is positive, then V1 is negative, okay? Okay. So then the difference is A2 minus A1 and V in here. So in this case, this is called differential mode, differential mode. So this DM is 2VD, okay, it's a 2VD. It's a 2V in, okay? Because then you have a A2 minus A1 times V in, okay, and V in for the differential input. So because you have two adding together, so you divide it by 2 in V in, you get this divided by 2. So divided by 2 because difference of the pair of differential inputs are twice of that each input, okay? So in this way, we can write V out in terms of the difference and the average, okay, and the average. So in this case, okay, V1, V2, if they are both, they are opposite, okay? So then your V out may not be exactly 0, okay? So if the ACM is 0, okay? VCM is 0, okay? Then the common mode so is always 0 because no matter what size here, V1 plus V2. So otherwise, if ACM is not 0, then the differential input will always got something extra, okay? Extra. So this extra is due to the non-identical and non-ideal case of the opamp. So therefore, ideally, ACM should be 0, and the CMRR is the ADM divided by ACM. It should be a very, very big value, okay? A very, very big value. So the bigger, the more desirable, okay, for differential amplifier. So CMRR is here, common mode rejection ratio, okay? So we have gone through everything with resistors only so far. From today, we are going to do reactive components with R and C, okay? But in the C is the capacitor is more important. Usually, if you do a physical L, okay, you have physical L, okay, then you need those coils, remember? Those coils. It is bulky, a lot of places you need to occupy. So your iPhone probably will need the inductors, but inductors can be equivalently realized by the capacitor. That is exactly the meaning of this one. Oh no. Meaning of the today's quiz, the last question. So you can see that in this op-amp circuit, your C is put in here. But from V and I relationship, okay, if you put the V and I relationship, if you look at here, okay, where's my pen color? It's okay. Still this color. So the whole thing here, you can see, is this component actually looks like a L. Okay. In other words, in integrated circuits, you don't have to have a bulky L, physically large. You can use very small capacitor to realize this L. Please derive this one and find out the L value here. So this is called a negative impedance converter. So then you should have the ability to find out how they are realized, okay? So that's why you see that in op-amp circuits, seldomly people using L. The majority of the examples they use capacitor. Okay. Okay, so this is a warm-up call for the complex in resistors. So it's called impedance. So basically, you have the same idea, and we call ZF and ZS. So these are called sometimes, okay, called impedance. But sometimes they add another term called impedance network. Okay, network is connections of other components. So this is familiar, but it's generalization to impedance. Now you can see things in here in this dash box. That's why we call this is a RC network. This is a network. The whole network is called ZF. Okay, it's called feedback impedance. Okay, we have gone through this already. Okay, okay, and we've also gone through the amplitude also frequency relationship. So if you have sinusoid in here, okay, sinusoids in here, so the amplitude is actually dependent. The amplification here is actually dependent. The amplification and magnitude here is dependent on how big is your omega. So you think about your omega can be tuned from small, from 0 to big. So it's from 0 to big. Then I check at different frequencies. Oh, like this frequency. Oh, then I can find out the gain is this. So the gain changes. So this is called frequency response, frequency characteristics of this filter. Okay, filter. And because in the lower frequency, the lower frequency part here, low frequency here is a one-to-one relationship. So they didn't get attenuated. And here, this is getting smaller and smaller because the higher frequency, they got attenuated. So in other words, we can say this is called high frequency rejection. I reject you, I attenuate you, okay? Rejection. So therefore, it is high frequency rejection or low frequency pass. So therefore, it is called low pass filter, okay? Low pass filter. So knowing low pass filter, everything on this slide is a very important indicator that you learn circuits and you learn mechatronics. You have some double E background. So if you don't even have a good idea about low pass filter, you basically cannot be a good engineer, okay? All right, so you learn vibration and control. Sometimes you need to attenuate some of the vibrations. So basically you need to have a high rejection, high frequency attenuation. Okay, so the same idea. So we can see what's the difference between here and here. So this is in the feedback. So we call this is feedback. What does the feedback mean? So this is output. I feed this one to this side. So this is called feedback. So this is the feedback. So that our ZF, the F stands for what? So I have a habit, always ask, oh, I have S in here. What S stands for possibly? S stands for source, okay? Source or sinusoid signal. Signal. Okay, source is better than signal. Or you can add together source signal, okay? F is like feedback network, okay? Feedback network, feedback. So then they swap the ZF and the Z1, ZS. They can, I'm so lost to what? Can you specify? Can you specify you lost on where? You lost a little confused on the concept of what? Low pass filter? Yeah, okay. Let me repeat what I said, okay? So this figure, x-axis is frequency, is omega, this omega. Remember you have sine omega t, okay? So remember you have sine omega t. Your omega, supposedly you have a knob you can tune. So the frequency can be low to high, okay? When it is very low, your frequency will be like this, okay? When you're very high, your frequency, your gain is like this, okay? When frequency is very low, your gain is like this. So that's why it's a high frequency attenuation and low frequency just as is, the pass, okay? The pass, okay? Just pass without, so basically this session says something like this: low pass filter allows low frequency part to pass without much loss, attenuation, okay? Right, so yesterday I also said like there's a corner frequency. like I think in the next slide I said that. So I'm pass. Here you can see stop. Okay, so you can see here. You can see here is a stop. So if your frequency, you tune the frequency here, the omega goes up very high, then you basically got attenuated as if it was stopped in here. You stopped. Don't pass to V out. V out is still 0. Okay, you didn't pass this. So it's like high frequency stop, but low frequency pass. Did you get it? Low frequency pass, high frequency stopped, or much attenuated. Okay, so therefore this is called low pass filter. Okay, low pass filter. Now we need to draw a line. Where is pass? Where is the stop? There's must a middle ground. Okay, middle ground. The middle ground is called corner frequency. You have like here you have turning point. Okay, turning point. So where's this turning point? This turning point is when your signal in and out, the power got reduced 50%. Okay, because the power reduced 50%, then magnitude is reduced by what? It's square root of the, because power is a signal square, right? So then square root of 50% is what? Okay, is square root of 2 divided by 2. Okay, and if you do the dB, it's a 20 dB, 20 log of 10, this guy. Okay, do you guys know what's this value? 20 log of 10, this one. Do you guys have an idea? Okay, so I don't have to compute. You guys can go there and use your computer. No, your calculator. So 20 times log of 10.707. There's a magic number here. It's called minus 3 dB. Minus 3 dB. Okay. So because this is a dB, so I know this minus 3 is here. Minus 3, drop 3 dB. So it's a 17 dB here. So this point is a corner point. When at this point, the frequency, the power will reduce 50%. The magnitude will reduce 2.707. I feel like this is a little bit confusing. We are going to talk about this one more, okay? So now we are switching here. Remember, I have a feedback network here is with RC network, but now I swap them. So here, this is the RC network. This is a pure resistor. So that one is a low pass filter, and this one is a high pass. Let's see it, okay? So let's do that. So it's the same, ZF divided by ZS. So, but ZS is simple. It's not in parallel, but in series. So this is in series, 1 over j omega CS. So this should be bracket, okay? Bracket. So you do a common denominator here, then you end up this one here. So then you use ZF divided by ZS. So this guy will stay here, okay? And this guy will in here times ZF. So you have this one and this one, okay? Okay. So as you can imagine, if my omega is 0, meaning this guy is a DC supply here. This is DC voltage. So that means this is 0. In other words, whatever this voltage is, you get this one here is 0. Okay, so it is not allowing the DC to pass this one here, because this is like a broken circuit. The circuit is broken. This is none, okay? This is a none. Okay. But on the other hand, if your omega is very, very high, very, very high, then the impedance of this guy is no longer infinity. Okay. So from here, for very, very high, then it will be like going to a constant gain, like this one. Because you divide it by omega, so this is a 1 divided by omega. So this goes to 0, then what's left is CS divided, cancels out, is RF divided by RS. And the negative sign is still here, so. Okay, so this is a high frequency, okay? So this is too extreme. When omega is 0, then I know that the gain is 0. When I say gain, that means it's V out divided by V in. Okay, then we talk about omega is infinity. I know my gain is minus RF divided by RS. This is the same as what we learned like inverting amplification formula, right? So you have inverting terminal here. Okay, so this is analysis through something what we called asymptotic analysis. Male is asymptotic analysis, like sending omega to extreme values, okay, extreme values. But what's in between? What's in between? In between, then you'll see that, oh, suppose this is sine omega t, then you change the omega, okay? So then we are going to see something like this. Okay, something like this. So you can see that this is log, this is log. So this is log, this is also log, okay? So dB. So this the reason we see this is more clearly, like straight line here, okay? But this one is a linear transition, okay? So I hope you can appreciate this two different scales. One is log plot, one is log plot. So in real world, we'll use this one a lot, okay? This one a lot. So you can see at high frequency, they pass. At low frequency, they stop, okay? Which is true. When this is a DC, very low frequency, DC, then there's a capacitor will stop the DC, right? Stop the DC. So this is a high pass filter. Shall we go back and check this low pass filter? Okay. So in fact, it's very interesting. Let me show you. In fact, high pass filter can be regarded as 1 minus low pass filter. Okay. Okay, 1 minus low pass filter. So that you swap, okay? In this case, okay, in this case. All right, so now you can see we have both coming in. You have RC networks in feedback loop. Also, you have RC network in here. So what are you going to expect? This is called band pass filter. Band pass filter. What does that mean? So remember, you have a low pass filter is something like this. Low pass filter is something like this. High pass filter is something like this. Okay. What if you say, no, I want something like, I want to stop here, but I only want this one passing here, then I stop again. So only inside an interval of omega. This is all omega. This is all omega. This is a magnitude. So I want the magnitude is not zero in certain interval. So this is called a band pass. This is low pass. This is a high pass. This is band pass. Okay. So we'll see what's this. So then we do the same thing about ZF divided by ZS. ZS is series. So this is okay. ZF, we also have seen this one is parallel. We also have seen this. So basically these two divided, okay, divided. So then you can imagine that you have this one is like high pass filter. This is a high pass filter denominator, low pass filter denominator, right? So the CS, this CS is the capacitor here, blocks DC or low frequency. So here is blocks, okay? This is 0. That the high frequency inputs go through. So it's a high pass filter. ZS, this is a high pass filter. ZF is a low pass filter. Okay, so low pass filter. Then in the high stop, the high will stop, low will pass. Okay, so low pass times high pass in here, cascaded. Okay, you end up with something like this. So then you have omega high pass. This is a frequency. This is omega is low pass. So it's called cutoff frequency. I already explained what is cutoff. When you have 50% reduction of the signal energy, signal power, sorry, then magnitude power is a square root of 2 divided by 2. Okay, so this is also a -3 dB. Okay, 20 log 10. 20 log 10 to the dB here will give you a 3 dB. So we assume that the high pass will be less than low pass. So then you end up with something like this, okay? Something like that. So attenuation here, or stop here. So pass here, okay? Stop, right? So in this case, you have a point in here. So this is omega HP. Omega LP is here. So these are called cutoff frequency. But how do I know where I put this dot? Yeah, you just here, you have a -3 dB here. So this is 17. This is 17. So you put a 17 dB line here, then you are going to get this. Okay, get this. All right. So 17 dB. So because this is dropping from here to here is -3 dB. -3 dB here. And 20 -3 dB is 17 dB, right? So this is a band pass. You may ask, oh, what if this guy is greater than omega? What if this one? So basically, you swap these two. What's going to happen? Okay. So this is called band pass because left and right are all stop. Okay, high and low frequency all get attenuated. Only small part in the middle will pass. It's called band pass. There is also something called band stop. Okay, band stop. So when you swap this one, this becomes a band stop filter. Then what we are going to see is something like this. So everything will get pass. Low pass, high also pass, but inside some of this one, so it's like a suddenly dip. So this is called band stop. Okay. So in this case here, this is a omega low pass filter, omega HPF. So you swap these two, you become something like this. Get it? Okay, band stop filter is when this two is so for in some cases, do you guys know this type of thing? So this type of thing looks like this. In real world, you can make things like this. You have something you pass everything, but suddenly you got something dip so deep, got attenuated. So sometimes I was joking. This is look like doing a acupuncture using a needle. Okay, so if you have a frequency at this frequency, I call omega 0. This is omega 0. You have this frequency, then your signal suddenly will get dipped. Means will be killed, okay, removed or notched. So sometimes this is also called a notch filter, okay, notch filter, okay, notch filter, okay. Notch filter is also called a band stop filter. Notch filter is the band is very narrow, okay, very narrow. At this point, I want to remind you that, so this is like second order circuits. So you have two independent storage element. So it's a second order circuits, okay? So it is not possible to have a first order circuit to be a notch filter. So notch filter, you have to have be second order or higher, okay? All right, question, let me see. Let me get, this is related to noise canceling headphones. The notch filter could be, but they may have many notch filters. So you have something like, you have something like you notch, maybe you notch, maybe you notch again. So maybe you have multiple notch filters to notch out those noises, okay? Notch out. So in this case, this kind of notch filter looks like every morning there's something you use for your hair. Go and Google and learn more. Comb filter, right? The comb filter, okay? All right. So this is band pass or band stop filter. So you have a two RC network, two RC networks, okay? Second order circuits. But what about, I have RL circuit in here and I have RC network here. So it's possible you have a second order low pass filter. So in other words, previously I showed you that you have something here, you have something 1 plus j b omega, right? A, B, and a constant. So you have minus sign here. But my question is, what if I put this one square? Is it possible? Sure. This is second order low pass filter. So I give you an example here as a low pass filter, second order. Okay. So in this case, let's see what's going to happen. So I have RL, ZS. So this is ZS. This is ZF. Okay. And we know this one already. ZS is R1 plus J omega L. So we know this. Then put together. So you have minus sign here. So this guy is 1 over S, 1 over ZS is this one. 1 over ZS. So ZS is this. So you get this. Okay. Others are just the same. So you can see in here you have two terms. What if you make these two are the same? L and C are the same, then you will be able to write a square root like this, right? So what's the difference? What's the difference? Why we need to even talk about second order? Well, first order is good enough. Is it? Really or not? So this is actually possible. You make this one the same, then you end up with something like this. So it's second order, okay? Why even bother about this? So V out Vs j omega, so it's called frequency dependent, okay? So it's a frequency response function, okay? So it's output divided by input. You may wonder, what does this mean, okay? Why write this one? I don't understand. Go and check the, if you ask the question I just asked, that means you need to read this file. I said, you must read this to warm up RL impedance phasor passive filters. So this is a deck of slides to summarize everything you are supposed to have already learned. I do know that phasor part is tricky. Many of you didn't really get it. I know it, but it's time to pick up. Otherwise, you will feel like what I'm saying here is another foreign language. Okay. All right, so let's continue. So again, ask a question. Why bother? We need to put a 2 in here. Why bother? What's the consequence? So it's a good idea to, when you learn how to question. Bring this question, then you create curiosity. Then when you get the answer, you will never forget, okay? So let me try. So this is the case. This is the case. So there's something called roll-off rate. Roll-off rate. So you can see the dashed line is a second order. The solid line is first order. Oh, no. Dashed line, this is the first order. We have learned the single RC when the, when the L is 0, okay? L is 0, when no L, L is 0. So this is a second order. What's the difference? Difference is the slope in here. Can you see? So basically, as frequency goes up, then it will start to attenuate. It's called roll off. Roll off. So this rolling off rate is minus 20 dB per decade. Decade from here to here is 1 decade. From here to here, decade is 10 years, right? So this is called dB per decade. Let's check. 20 dB per decade. Then from here, let's see, 3 decade is 60 dB, right? So this is, they did this 20, this is 20 dB, this is 20 dB, okay? 20 dB to 20 dB, you start to roll off in here. So then 1, 2, 3. So then this should correspond to about 20 dB. So then it should be 60. So this should be like 40-ish, okay? So this is the 40-ish, minus 40. So 20 to 40 is 60. So I have 3 decades. So this is a 1 decade, 1 decade, 1, this is 2 decade, 3 decade. The 3 decade in here, this should be corresponding around 40. Then 40 plus 20 is 60. So you should times 3 times 3, right? So it's 60 dB per 3 decade. Okay. So, but here is like you have 3 decade in here, you should have 120. So this is a 100, right? So this is a 20. So here is 120. You also 3 decade, you got 120 minus 120 dB per 3 decade. Okay, 3 decades. So in other words, the unit is, so this is the roll-off rate is, the slope is minus 40 dB per decade. So while this guy is minus 20 dB per decade. Okay, per decade. So in other words, they will attenuate faster or stronger. In other words, your echo cancellation for those high frequencies are more effective. So you may wonder, so that is answer your question, the roll-off is faster, okay? Roll-off is faster. So that's good, that's good. So, but the question is, can this one be even bigger? What's the consequence of the when this is bigger? Okay, so you can do another one like this. So this one has a price to pay because the lag of the phase. We are going to explain in the Bode plot, maybe 2-3 weeks later, about signals and systems and frequency domain characterization. We're going to learn how to plot the Bode plots, sketch it, read it, so on and so forth. Okay, so this is just give you a flavor of frequency contents of a frequency. So this is built on some concepts of phasor. Okay, phasor. So you have a V of S is a sinusoid. Okay, then the omega can be bigger or smaller. Then we see how the gain, this is the gain, how the gain will change, They also, this is this is called a transfer function, a frequency response transfer function, the gain, complex gain. So complex gain here, we only plot the amplitude. What about phase? Okay, so you have amplitude and phase together are called Bode plots. We are going to do that later. But today we got appreciation that using RC circuit, using our LC in the opamp, we can have active filters. Okay, active filters. You can have higher order filters. The higher order will achieve bigger roll-off rate. So for you only have first order, you have minus 20 dB per decade. You have second order, so this is a second order, so you have minus 40 dB per decade. All right, so before we end, we are going to finish by introducing another 2 important circuits that is doing differentiation and integration. We learn integrator first, because this is widely used in op-amp circuits. So this is called an integrator. So low pass filter is actually, the integrator is like a low pass filter. When you have remember we put a resistor here, this becomes ZF, and when we have this R is infinity, okay? This R is infinity. So it's broken circuit. So it's broken. So we have this CF alone, okay, alone, okay. So this is called integrate, okay, integrate. So integrator of what? So let's do derivation. So again, this is inverting terminal, okay? Inverting terminal. We do a KCL at this point. So we know that IF plus IS equals 0, okay? IF plus IF is 0. Why? Because this is ideal op-amp. This current flow into this is 0, okay? 0. So virtual ground. So this is a ground. Okay, G and D. So this is actually VE, the virtual Earth. Okay, virtual Earth. So because of that, IS is VS divided by RS. So this is Ohm's law. Ohm's law. The capacitor, this is a capacitor's what? Constitutive equation. Constitutive equation. So don't ask me why this is the case. Capacitor is doing that. So we have this one, then we know that VS and RS, you have this V out. So what is considered as a system? When you have a system, you need to define what is your input, what is your output. So this is in, this is out, okay? So then we can write it in a black box. So this is in, this is out, okay? So out divided by in, okay? So out is written as in terms of in, okay? So in this case, I have integration operation of the input signal. Basically, my output is the integration of my input. My output is the integration of my input according to this derivation. Then basically you write everything in this form. So all other things are just, sorry, this is the CF. So these are just constants, okay? It's called integration gain, okay? You don't have to be 1 or whatever, okay? So this whole thing is called ideal integrator, okay? Integrator. So again, the opamp helped to make an operation of mathematical operation. And here is just integration of the integral, okay? So that's ideal integrator. So next, did you see we swapped the position? The R and the C, swap the position. So we put a C in the beginning, in the input. So then what I'm going to do is the same thing. We apply everything the same. So in the end, we can see that the output is a differentiation of the input. Okay. So in other words, I have a box in here. So basically I have in signal, V in is V out. Okay. Then here I just do ddt. So this is an operator, right? Don't worry about the negative sign and also the coefficient, right? So you can always assume this is 1, like you are doing here, okay? All right, don't argue with me. Without, without loss of generality, V log, okay? Without loss of generality, okay? Generality. So basically, ideally, I have V out is a ddt V in, okay? All right, you can absorb the minus sign here. You can have an inverse of this value multiply and you get 1. So that's easy, right? All right, so I'm curious. Then you have this differentiation. Then what is the frequency response? It's a j omega. Okay, it's a j omega. So in other words, if I want to draw a magnitude in here, so this is j omega, magnitude, okay? So this is my omega, right? So in other words, my magnitude of differentiator is, so this is 1, omega is 1, this is also 1, this is 1, 1, okay? Okay, so it becomes like this, okay? So this is magnitude, okay? Math. So it's a straight line, okay? It's a straight line passing through this, okay? But what if passing through 1, if 1 omega is 1, the magnitude is also 1, right? But what if I plot this one with log? I have a log omega, okay? So this is a j omega here. This is a 20 log 10 j omega magnitude. So then you will see this is a 0, and this is, when this is 0, then this is here is also 0 dB. Then it's 0, 0. They pass this one here. So, but basically it's still 1. Omega is 1. Then this is 0 dB. Because log of 1 is 0. 0 dB is okay. So you have something like this. Okay. So the same thing is straight line. Okay. Same thing is straight line. Okay. Then I'm curious, what is this one? So this is plus 20 dB per decade. Okay. Plus amplification. So if your frequency is very, very high frequency, very, very high, then your amplification magnitude is also very, very high. So in other words, if you do a circuit only like this, what's going to happen? So if you have any noise in here, and this noise will, because it's very high frequency, it will be amplified huge. So this is amplified noise. Amplified noise. So this differentiator is actually a noise amplifier. Will make your noisy signal even more noisier. So it's usually that's the price you need to pay for differentiation. Similarly here, go back, if we wanted to see here, you have something like this. So this omega, this is 1 over j omega magnitude, okay? So here you also have minus 20 dB per decade, okay? So, and this one is always goes way up, okay? So the lower the frequency, the higher the magnitude. That means if you have a DC bias and DC signal, it will get amplified huge, okay? Amplified huge. That's integrator is to make a control system to suppress your bias. Anything like you have a bias, then will make the bias go to 0. Because if you have a bias, then we'll keep adding together to suppress your bias. Bias is a constant bias, then it's like a DC bias, okay? Direct current bias. We are going to mention this one later, okay? So with that, next 5 minutes, we are going to review some practical issues, okay? So practical issue is, well, I said this before, but I want to visualize it for you. So usually you have VS and you don't draw this usually, right? But it is there, it's a 50. So if you do amplifier, yes, you can, but if you do a amplification about 20, so then you got a 20 sign. This part will be chopped off. So this solid black line is the actual response. So anything above 15 or below minus 15, it will be chopped off or saturate, okay? Just stay the maximum. So remember this. So therefore, your power supply, the 2 is too big, magnitude is too big, or your amplification gain is too big, okay? RF divided by RS, this is probably not a good combo, okay? not a good combination. This gain is -10. Don't forget this minus, okay? This is an inverting amplification, okay? So that's one thing. Frequency response limit, okay? So any of the frequency, in reality, we say this is a very big number. It's infinity ideally, but in reality, this magnitude of the open loop amplification is like a low pass filter here. So there is also a finite bandwidth. If the omega is too big, then the AV will be small, will roll off. So this is called a roll off. Okay, will roll off. Okay, will go down. Okay, will go down. So this, when you buy an op-amp, real op-amp, they will give you this figure to tell you if your signal is too big, then it will be the real magnification, open loop magnification will be small. So in this case, usually they are going to give you A0 times omega 0. This is the first roll-off cutoff frequency, cutoff. So this is also called, so don't say you haven't learned this term. It's called gain bandwidth product, okay? It's A omega 0. So omega 0 is here. It's A0 omega 0, okay? Gain product, okay? All right. So you should, when you buy an op-amp, you should do CMR. You also check this one, okay? Gain bandwidth product. And this is low pass filter. You have learned this low pass filter. Low pass filter in a log scale. This is log scale. Okay. So physical limit, saturation, frequency response limit. There's a very important thing called gain bandwidth product. So usually this is actually quite high, and you're playing your signal. Your signal probably is way lower signal in this range. So this is called your frequency range of interest. It's well within the omega 0. So you don't have to worry, but better to double check, okay? So I got the slides from this person, and when I try to come back, and I cannot find him anymore. So I feel very sorry, but I still put here, give him the credits. So we use up the time, finish the op-amp this module. I think we are doing so fine, and do spend enough time on the homework number 4, focusing on op-amps in 2 categories: op-amp with resistors only, and op-amp with L and C. So after you finished all this, I believe you are ready for the next module. So the next module, we'll have 1 more minute. So next module will be, so we should worship our syllabus here. So week 5, we are going to go to signal and systems. You actually already are doing a modeling and a simulation, but we really need to go through the basics, okay? Basics, especially the realization part. And now many things will make very good sense after you have learned these 3 weeks contents in the signal systems. Then we are ready to go to controls. Then we do a spring break, and we are going to have a take-home midterm exam. You do it by your own, and have a busy spring break to pick up everything we have learned here. After that, will be do digital controls, talking about sensors, actuators, and put everything together towards the future. See, all these are just the mechatronics basics. Any questions? So we only have 47 students showed up. So this is not a good number. I don't like it. So I know that you say, how many questions in the midterm? It's about 10, okay? I know some of you may say that you are going to pick up the YouTube watching. But from my checking, I can see how many students watched. Not many, okay? So please use your time wisely. If you can make the lecture, you should make the lecture in synchronous mode. Try to be self-disciplined, managing your time. Questions, chats? Is the exam for the who do? Nah, but possibly that midterm will spend 2 to 4 hours long, depending on whether you are feeling rusty on the many parts. It should be straightforward. It's not that hard, okay? All right, so let me see one more question. The whole spring, yeah, you have a whole spring break to finish the midterm exam. It's forced you to go and visit everything you have learned so far until week 10. So, all right, we have 2 minutes over. I want to say goodbye to you. Again, Happy New Year of Ox. Bye-bye. Bye-bye.